All right, so today's topic is topic 3, which is separating Earth's mixtures. All right, so we've talked about mixtures quite a bit, what they are, what they're composed of, and so on. We've talked about solutes and solvents and so on. And today we're going to talk about how to separate mixtures. So sometimes we want to separate mixtures back into their components. So when separating a mixture, it's useful to know the properties of the components and how the components differ from each other. So for example, how could we separate gold from the other components in that ore? So it's useful to know the properties of gold and the other properties of the ore so that we can separate the gold from the rest of it. All right, so here's an example of desalinating water. So removing salt from water is very, very important because in many parts of the world, fresh water is very scarce. So seawater has to be desalinated to provide drinking water. All right, so some parts. All right, so like I was saying, many parts of the world, fresh water is scarce. So seawater has to be desalinated to provide drinking water. So this is a simple method. It's called the desert tent method. So it's a cheap method, but it is very, very slow. And it only works where there's lots of sunlight. So what's happening here? You can see the impure water here. So the salty water is in this container here. And then there's this clear plastic sheet kind of in this tent method. And we have the sunlight reaching right through that clear plastic sheet. And then the energy from the sun is going to cause that water to evaporate. Once it contacts this cooler plastic sheet, it will condense. So condensation will occur and you'll end up with pure water here on either side of that tent. All right, but like I said, it's a very slow method, but it is a cheaper method than what we'll look at next. We're going to look at distillation in just a moment. So dehydration is a process of removing water from a solution. So for example, dehydrated foods like some pastas and sauces and some milks, those foods have been dehydrated by removing water from the solution. So next we're going to look at distillation, which is a separation method that allows all liquid fractions of a mixture to be separated from each other and then collected in different containers. So there's evaporation involved. So it involves evaporating a solvent to separate it from the solute and then condensing it back to its liquid form. There's water circulating in a condenser, which helps cool the steam as it passes through the tube. So we're going to look at an example of distilling water using distillation. So again, we have that impure water here. We have the seawater and it contains salt. So we're going to heat that up and it's going to form into steam. And that steam will then go through a condenser, which is this tube here. And there's usually some sort of cooling technique in this condenser, usually cold water. And then on the other side here, we will get pure water. This is also useful with processing petroleum. So petroleum products such as kerosene, gasoline, diesel oil, they're all burned to produce electricity and move vehicles and so on. So fractional distillation is a process that yields different petroleum products from crude petroleum. So crude petroleum is the raw material that is being pumped to the surface. So this mixture, it's a liquid solution, and we heat it up and one part becomes a gas. That gas is going to travel up and away from the heat, and then there's a separate chamber. The gas gets cooled back into a liquid, so it recondenses. That recondensed liquid is then collected in a separate container. And eventually, all parts of that liquid solution, it will vaporize and recondense in a separate chamber, and then it'll be collected in separate containers. And keep in mind that each substance in this process, they condense at a different temperature. All right, so here is a quick video we'll watch on fractional distillation. And then we can also see here in this diagram how we can see all these different parts condensing at different temperatures, and then they're being collected in the containers. All right, so this example here is solid mixtures from underground. So most underground materials are solid rock. So when we talk about an ore, it's a mineral or a group of minerals that contains a valuable substance. So for example, gold ore, it's a mixture of two pure substances. So in this case, white quartzite and yellow gold. So the ore is blasted and crushed. The ore powder is then mixed with water to create a suspension. And then certain chemicals are added to dissolve the gold. And basically anything other than gold, it will not dissolve. So then it goes through filters. Only the particles dissolved in water can pass through the filters. The rest, which is solid waste, will get caught in the filters. Then zinc is added to the solution and gold is released. And that basically that gold residue, it'll sink down to the bottom, and then it's carried and collected in a collecting tray. All right, we have a couple of videos here on separating mixtures. So there are quite a few methods of separating mixtures. So again, it's important to know what properties those mixtures have. So for example, if it's iron, iron is magnetic. So you can use magnets to remove iron. Some substances are able to float. So therefore you can immerse the substance into water, and the substances that can float, then they can be picked out. We also talked about fractional distillation. We talked about distillation. And these couple of videos here will also explain some other methods of separation.
Your cell phone is mainly made of plastics and metals. It's easy to appreciate the inventive process by which those elements are made to add up to something so useful and entertaining. But there's another story we don't hear about as much. How did we get our raw ingredients in the first place from the chaotic tangle of materials that is nature? The answer is a group of clever hacks known as separation techniques. They work by taking advantage of the fundamental properties of things to disentangle them from each other. Simple separation techniques apply to many physical scenarios, like separating cream from milk, extracting water from soil, or even sifting out flecks of gold from river sand. But not all mixtures are so easy to unravel. In some of those cases, we can exploit the differences between physical properties within a mixture, like particle size, density, or boiling point, to extract what's required. Take petroleum, a mixture of different types of hydrocarbons. Some of these are valuable as fuels, and others make good raw materials for generating electric power. To separate them, experts rely on one important feature. Different hydrocarbons boil at different temperatures. During the boiling process, each type vaporizes at a precise point, then gets separately funneled into a container and collected as a liquid as it cools. Separation techniques also take us to the sea. In some drought-stricken countries, the ocean is the only available water source. But of course, humans can't drink salt water. One way to get around this problem is to remove salt from seawater with reverse osmosis, a process that separates water's ingredients by size. A membrane with pores bigger than water particles but smaller than salt particles only lets fresh water pass through, transforming what was once undrinkable into a lifesaver. Meanwhile, in the medical world, blood tests are a vital tool for evaluating a person's health. But doctors typically can't examine blood samples until they've separated the solid blood cells from the liquid plasma they're dissolved in. To do that, a powerful rotational force is exerted on the test tube, causing heavier substances with higher density, like blood cells, to move away from the rotational axis. Meanwhile, lighter substances with lower density, like plasma, move to its center. The tube's contents divide clearly, and the blood cells and liquid plasma can be tested independently. But sometimes, unlike oil, seawater, and blood, the parts of mixtures that we want to separate share the same physical properties. In these cases, the only way to isolate ingredients is by chemical separation, a complex process that relies on unique interactions between components within a mixture and another material. One of these methods is chromatography, a tool forensic scientists use to examine crime scenes. They dissolve gathered evidence in a gas and can monitor and analyze the ingredients as they separate and move at varying speeds due to their unique chemical properties. That information then tells scientists precisely what was present at the scene, often helping to identify the culprit. Separation techniques are not just about industry, infrastructure, medicine, and justice. One of the most technically ambitious projects in human history is a separation technique aimed at answering the fundamental question, what is the universe made of? By accelerating particles to extremely high speeds and smashing them into each other, we can break them into their constituent parts, ever so briefly. And if we succeed at that, what's next? Is there a most elementary particle?
A solution is a mixture of two or more substances in the same phase. This is formed when a solute dissolves in a solvent. A solution can also be formed when two or more miscible liquids are mixed together. When ethanol and water are mixed together, a solution is formed. Now, how would we separate these solutions? To separate dissolved salt from water, we would simply evaporate as much water as possible, leaving behind white salt crystals. The separation technique is known as evaporation. To separate ethanol from water, we must take into account the fact that these substances have very different boiling points. Water boils at 100 degrees Celsius, whereas ethanol boils at 78 degrees Celsius. This mixture can be separated by simple distillation. The lower boiling point component, in our case ethanol, will evaporate first. The ethanol vapor condenses as it passes through the condenser, and the distilled ethanol can then be collected in the receiving flask. The above mixtures are homogeneous mixtures. This means that the components of the mixture are in the same phase, or the composition of the mixture is uniform throughout. Now, we will look at separating heterogeneous mixtures, where the components in the mixture are not in the same phase or the composition of the mixture is uneven. If we have a mixture of sulfur and iron filings, we can easily separate this mixture with a magnet. The magnet will remove all of the iron filings, leaving behind the yellow sulfur powder. We know that salt is completely soluble in water, but sand is not. How would you separate a mixture of salt and sand easily, keeping in mind the solubility of salt in water? Pause, think, and continue when you have an answer. The salt and sand mixture can be added to water. Salt will dissolve, but sand cannot. The resulting heterogeneous mixture can be filtered through a funnel lined with filter paper and washed with water to remove as much salt as possible. The substance that remains on the filter paper is known as the residue, and the substance collected in the flask is called the filtrate. For our case, sand is the residue and the salt water is the filtrate. The salt can be obtained using evaporation and the sand left to dry. The same method is used to separate a suspension, which is a mixture of an insoluble solid in a liquid, such as, for example, small bits of chalk in water. Two immiscible liquids, such as oil and water, can be separated using a separatory funnel. This is an apparatus with a stopcock at the bottom. Releasing the stopcock allows the contents to flow out, and closing it stops the flow. To summarize, there are many different techniques to separate mixtures, all depending on whether the mixture is homogeneous or heterogeneous.